for this thing. So I'm saying it in a slightly general picture. Okay, then it will be more clear. Rings is something which you know, right? So I'll say rings with Fermat identity. Okay? So maybe I can ask you a question first. Yeah. So can you give an example of a place where you have addition, and can you give an example of a ring where a to the power p is equal to a?
Just thinking, wait a minute.
Yes, yes. Here you can take p to be a prime also. So just take some simple example, mod p or something.
Then it would be mod of p minus 1.
Not.
No,
Mhm. So what is your set?
your identity equal to 0 or 1? Like it's
What is
which
0 or 1?
identity we will be taking? Like the multiplicative identity or additive identity?
Oh no, sorry. This identity is not that identity. This identity just means, so we leave this. Yeah, just think of a ring in which this is true. I will explain that then. But think of in a ring in which this is true, right? So you can take this ring, right? You can take z mod pz. Okay, basically integers where addition and multiplication is in modulo p, right? Just a simple, and not even write plus. You know what all those operations. So in this ring, this is true for every element, right?
Yes.
Yeah, that you know, and if you don't know the proof, then do a proof by yourself, right? It's a standard thing, right? It's called Fermat's theorem, right? Fermat's-Little theorem. So z mod pz. So in z mod pz, a to the power p is equal to a for all a, right? And so this is basically and this becomes an identity in the sense of the high school identity. Prove this identity: if a plus b whole square is equal to a square plus b square plus 2ab. So this also is an identity because it is true for every element a, right? So this is Fermat's little theorem. You can just read the proof somewhere or do it yourself. I'll leave that for you. It's not a boring one, but I'm just doing it because it's a standard thing. So I'm not doing the proof. This thing. So this kind of identity we can call Fermat's identity. Okay. Can you? But let's see. Let me give you an example of another ring where this is true. Okay. So are you fine with it so far? What I'm saying this in the language of ring? Yeah. Just one thing that you see that this is not like this can be stated without any without referring to any addition operation. That's a nice thing. Okay. Yeah. This kind of identity is nice in that sense. So even you can prove it using group theory, using Lagrange theorem and so on. But you can do an elementary proof also. But anyways, now look at this ring. Okay. Look at this ring. Z mod PZ cross Z mod PZ. Okay. So what does this mean? This just means that as a set, it is the Cartesian product, right? And the operations are coordinate wise,
Mhm.
right? You are just the natural things. In this also, this will obviously be true, right? Because and this is I'm just not doing anything. So it's just to the power p. By definition, this is becoming like this. This is by definition of the multiplication that we have defined on the product. We are assuming on the product you can give many kinds of new structures, but we are just taking the normal one, right? So this was an arbitrary element, right? This is your x and this is your x, obviously. So x to the power p. Okay. So these are the rings in which this Fermat's identity holds. Okay, so this is just a small thing I wanted to say. One second. This can potentially be a very vast question, and I don't know the answer to that also. Can you think of any other example? So P is a prime here, right? P is a prime. Can you, so let's keep P a prime only and ask questions. Okay? P be a fixed arbitrary prime. Okay? You should pay attention to these rings and you should pay attention to the proofs of these things because they will be very, very useful in group theory. And later you'll be doing matrices over finites. These are finite rings. And these questions are quite favorites in this for MCQs. Yeah. So you should pay attention to these rings. Um, yeah, I can say some things, but it's not very useful. Oh, 1 minute. Right. So maybe I will not say anything. Yeah. But then let me say some things about these things where we go from rings to fields. Okay. And uh, yeah. So let's go to fields and also see the relation of these things. Yeah. Fields. Because you know that Z mod PZ is a field, right?
Yes, 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 it's a field.
It's a field. It's a good exercise. Z mod PZ is a field, and of course you have that identity also. So as in a field, the field also it will happen because the operations are the same. You can notice one interesting property of this field. Okay? So characteristic of this is also fields, which means you can consider vector spaces also over these things. But characteristic of Z mod PZ. So do you know what is characteristic of field yet?
Uh, Characteristic field. They are both group under addition and multiplication.
No. That's right. That's the definition of a field, right? I'm not asking for definition of field. So there is something called so with every field F, we associate a concept called characteristic.
Okay.
So yeah, so what is that? So given a field F, so given an arbitrary field F, you know the definition, but then you look at one in the field. Okay, there is a one which is the multiplicative identity. Yeah.
Hmm.
And now you look at the order of one, yeah, with respect to,
Hmm.
obviously with respect to addition, because with respect to multiplication the order is just one, right? So with respect to addition you look at the order. What does it mean? It means that you look at the smallest a such that a times 1 is equal to 0.
Okay. That sorry, I forget actually
That's
that.
characteristic, right? Yeah.
Yeah,
So
yeah.
it is the smallest number a such that a times 1 is equal to 0, right? Yeah.
Hmm.
Basically, these are the field theory that you need to know. You don't need to know any high-fi field theory, more field theory, much more, little bit more maybe. So that's a characteristic of a field. Okay, you can go back and read it. But so what is the characteristic of this field?
Is equal to ZP. So um, one to any element. So for all element, P.
Perfect, right? Characteristic is P. Right. Yeah. So this is a field in which the characteristic is P, right? These kind of fields are, they behave differently from the rational numbers, right? And they can be new sources of examples. And now let us try to connect this with that property. Right. So you see, this is happens in this field. Now just compare it with an arbitrary field. So F be a field, again arbitrary in the sense that F be a field of characteristic P. So not necessarily this, but this is an example. Okay. If F is a field of characteristic P, then you can easily show that A plus B to the power P is equal to A to the power P plus B to the power P. Right? This is a homework. Should show this. Okay? Not very surprising, because the P choose 1 is basically P, that becomes 0. P choose 2 also becomes 0, because the characteristic is P. Okay, so you should try to show this. Maybe I will not try to show, you should just write it and try to show it later. This is a very good identity, right? So this is basically property number 1. Okay. What is another property which I want to say about this field? And we'll arrive at this very soon, so you will see. F is a field of characteristic P. Yeah. So then show that Z mod PZ is contained in F. This I'm just explaining now, because otherwise it's a little different type of question. What do I mean? I mean that you look at this F, right? And look at the element 1 in F, right? And then you look at this element 1 plus 1, and look at this element 1 plus 2, 1 plus 1, sorry, 1 plus 1 plus 1, and similarly P times, right? Look at this collection. I mean, of course, you just write this usually like this, right? Of course, this P is your 0, right? This P is your 0, and these are the elements, right? Obviously, all these are there in F, right? 1 is there in F, so
Yes.
all these things are there in F because the characteristic is P. And then, of course, when you multiply multiply the things in this, they remain in this set.
Yeah.
Right?
Hmm.
Yeah. So let me explain this separately. Next mode. So what the claim is, setting is as before. We'll just connect this with that, and what I'm trying to say is that you take any field of characteristic P, it will contain Z, a copy of Z mod PZ. It is built on Z mod PZ. Okay. For example, you know this fact that if you take any field of characteristic 0, then it contains the rational numbers. Right? Because it contains 1, so it contains 2, 3, 4, and it contains all the integers. Right? Because 1 times anything is not 0. Right? Characteristic 0 means what? Characteristic 0
It's
is a means it's never 0 basically. It's paradoxical in that
yeah,
sense. But
1.
yeah, exactly. So 1 times anything is not equal to 0. If A is not equal to 0. Right? So that way I'm talking about. So you know that fact that if you have a field of characteristic 0, then it contains the rational numbers. You can try to prove it. Similarly, I'm just saying that if you have a field of characteristic P, then it contains this Z mod PZ. Okay? So F is a field of characteristic P, then it contains Z mod PZ. And I'm just trying to explain why. So clearly this thing, this is actually equal to 0. This thing is contained in F, right? And this thing is nothing but Z mod PZ. Okay, because it forms a group, right? If you take any two things in this, for example, you take let's call this first A. Okay, so you take X and Y in A. Okay, now what is X? X is basically 1 plus 1 some number of times, right? Some number of times. And similarly, Y is also 1 plus 1. You may think why I'm overwriting it, but it's because a priori you don't know. So X and Y are these. So when you multiply this and use a distributive law, right, it just becomes 1 plus 1 plus 1 more number of times, right? If this thing is m times and this thing is n times, then this thing becomes mn times, right? And obviously mn mod p, right? Because mn times, and if mn is more than p times, then the blocks of p become 0, right? 1 plus 1 plus 1 p times, that's 0. So we forget, and to understand, right? For example, as a small example, I'll say, for example, you take p equal to 7, and you take x equal to 2, and y equal to 3. Then obviously x dot y is as you expect, it is 6. So in this case, you sort of have to prove it because, yeah. But if this is equal to, if this is 4, then x dot y will be 8. But that 8 will actually be equal to 1 because we are working mod p, right? Or when you expand this, you will have 8 ones side by side, and 7 ones will be 0. And so it's 1 plus 0 is 1. Right? So either ways you want to think, it's, yeah, it works. Right? So why did I say this? I'm saying this just to say that this thing actually is a group, right? It is a group under addition. Under addition, it is a group. Sorry, I mean, yeah. So it's a ring, right? It has a addition, it has a multiplication, it has everything, and so it is precisely this thing, right? Because this thing also has the same properties. I mean, I can say all this in terms of isomorphism and so on, but you understand the point, right?
Yes, yes.
Yeah, like something needs to be said that a cyclic group of order P is unique up to isomorphism, but you understand the points. I'm not trying to be rigorous because that's not what our main aim here is. Okay, so roughly, so this point is then fine that it contains Z mod PZ. Okay, this is a nice thing. Now, now you see. Now I'm just saying that use number 1. Okay, use number 1 to show, okay, that 1 plus 1 plus 1, if it is k times, okay, to the power p, Okay, then this is equal to 1 plus 1 plus 1 k times. I'm asking you to prove it using 1. This is homework. It just requires some manipulation. Okay, maybe some induction or something.
Okay.
Okay, you can see that this is basically what we are talking about here. Right? So for every element of f, which looks like this, which is 1 plus 1 plus 1 added k times, right? Every element of f which looks like this thing, which basically means every element of f which comes from here, right? Every element of f which comes from the z mod pz satisfies this identity. Not every element of f, only those which come from them. Okay, right?
Yeah.
Okay, so this is a nice nice thing, right? Yeah, we basically have proved this in that way. It's proved because you can just take f to be z mod pz and done. But that's fine. Now let me also give you some more homework. So this is some field. You can see that all these things are quite close to each other. All these things are quite close to each other, and then yeah. So if you know the definition of vector space, show that f is a vector space over z mod pz. But that is not the important question. Yeah, the important question was show that x to the power p equal to x implies x is in z mod pz. Okay, so x in f. So you are, so now you see you're going the reverse. You're saying that you take an x which is in f, which is in this larger field. Okay, and maybe I should give you an example of such a field, but maybe I'll not do that today. You take a larger field, okay, which has characteristic p. You take an x in this which satisfies this Fermat identity. Then we are saying that x is actually back in the base, back in z mod pz. Means that x is basically, I'm just asking you to show that x is basically 1 plus 1 plus 1 some k times. Yeah, it's a converse of 3. Right? In 3 we showed that
I
every
didn't get that.
right. So in 3, what did we say? That so is this picture okay? That this f is there, and so there is f, and there is z mod pz sitting inside it.
Yeah.
That picture is fine, right? So there is f and z mod pz is sitting inside it, and we exactly know what it is. It is 1, 1 plus 1, 1 plus 1 plus 1, and those things. That's z mod pz. F and z mod pz. So we have shown in 3 that every element that is in z mod pz satisfies this nice identity that the pth power of that is again the same thing. Right? That's number 3, which you have to do using 1. Okay. But now now if you look at number 5, it is saying that if anything satisfies that identity, if anything in that f satisfies that identity, it's actually in z mod pz. It's actually in this. So nothing else apart from things in this satisfy that identity.
Okay.
Okay, right. So exactly. So basically that set z mod pz can be defined as those things in f is satisfied this identity. So that will give you exactly that. Okay, this is going to be very crucial, very crucial. So that's why it's important to note this. And yeah, just do these things, and that's all. And then you see, right? So if you are in z mod pz, if you are in z mod pz, then those kind of things which you were saying, right? U to the power p or whatever square, this is equal to uv. Then it's true, right? Because u to the power p you can replace with u. That is a reason why all these things you can do. Okay. Yeah.
Okay.
Okay. Yeah, those kind of things is the reason. yeah, these things are slightly abstract. Yeah, there is a lot of things here. If these fields are very, very strange objects in some sense, but not also. But they are not strange, but they say anything. Okay. So yeah, let's use the next 3 minutes to do the next problem quickly. So look at the next solution quickly, and then we'll take a break. Here, so I was reading. So A is in R. So first you are assuming that it is Z mod NZ. And what do you want? You want to prove that n is a prime, right? So you are assuming that every element is nilpotent A. So but then therefore there exists B. So why? Why? So you are saying that A is invertible?
I just took first the elements of R is invertible, and
But
then
you did
showed
not write
that
it, right?
the
No. So
no.
are you assuming?
I
So
just
you are
nilpotent and invertible. I just choose the one invertible.
you choose. So you are assuming A is invertible.
Yeah.
Okay. So you should write that. Otherwise, it's not clear. Yeah. So you're saying okay, let A be invertible. So then, what are you trying to show after this?
I just took one here. AB minus one equal to some scalars into
Right.
n.
Wait. So this thing, no, but it's not correct. Right? AB minus 1 divides n. How do you
Yeah.
get this?
I just wrote there AB minus 1 equal to k times n.
No, n is equal to k times AB. Okay, but you wrote it the other. Okay. So this thing is not the standard notation, right? When you say that AB minus 1 is a multiple of n, this is written as n divides AB minus 1, right?
Yeah.
I mean, this is your own notation, but it's not the standard notation, right? Okay, so now that's not a problem. So this is this, and this is this, and this implies the GCD of A and n. So why is n a prime then? Prime number?
It's something called B.
No,
Some
but
theorem.
that's not what that theorem says. That is Bezout's theorem, I think, but that is not what it says, right? No, but I don't understand. So you forget the theorem. Forget the theorem. If GCD of A and n is equal to 1, n is a number, A is a number, GCD is equal to 1, how does that make n a prime number? Just no, right? 2 and 2.
So why n is prime?
Yeah, you have written n is a prime number where n is equal to this also, but that doesn't make any sense, right?
Because I took the A is an arbitrary element from R.
No, A is not arbitrary. You assume that it is invertible. So you didn't understand this statement then. This statement, okay, we'll meet after 5 minutes and we'll discuss this. This means that some elements of A might be invertible and some elements of A might be nilpotent. So
Yes.
it's in the understanding of the statement. You assume that every element is invertible and every element is nilpotent, right? Okay, we'll discuss this. This is important to discuss. Yeah, so just then think about it. Okay, and then
Okay, if we just take that
the meeting will end.
the
Meeting will end.
invert.
Yeah, the meeting will
Okay,
just
okay.
end. So think about it. Yeah, some are invertible and some are nilpotent, and then you think, yeah, but there's no third type. That's all.